And we'll continue where we left off yesterday. We were doing an example about this motion using the fact that we have acceleration due to gravity, and that if we know the acceleration, we can find the velocity vector by integrating. If we have a velocity vector, we can find the position vector by integrating. So we were working on a problem that had several parts. We just did the first part. It's the most important part anyways. So let's recall what this problem was about. Let me go to the page. We have this situation over here. Let me recall you. This is what the problem said. It says a baseball, this one over here, is hit 3 feet above front plate. So this is 3 feet with an initial velocity in feet per second of 80,80. So this is the initial velocity. So a vector that is 80 in this direction and 80 in that direction. As I told you before, my picture is not, it doesn't have the right scale, because if this is 3, then 80 should be, I don't know, all the way over here, right? But then it wouldn't fit on the page. So it's a big vector pointing in this direction, 80. And then once you hit it, it goes like this, right? And that's what we need to find out. And the only physical consideration that we need to observe is that the acceleration due to gravity is given by negative 32 feet per second squared. So that's this force that it's always pushing in the down direction. So always going down with a magnitude of 32 feet per second squared. And because it's going down, we have it as a negative. So, and then that's pretty much all we needed to figure out both the velocity and the position of the object. Here we go. So because we know the acceleration is the derivative of the velocity, then we could get the velocity by integrating the acceleration. Now, to integrate a vector function, you just integrate each one of your components. The integral of 0 is just a constant. I call it C1. The integral of negative 32 is negative 32t plus this constant C2. And then to figure out the constants, we use the initial condition. We know that at time 0, we hit the ball with this vector, 80, 80. So this 80, 80 has to be the same as when you plug 0 in here. When you plug 0 in here, you get this term that cancels. Then you get C1 and C2. So this tells me that C1 and C2 are both 80. And then here's my velocity. My velocity function is 80, negative 32t plus 80. Now, to keep going, to find out the position of the ball, where we note that the velocity is the derivative of the position. So to figure out the position, we need to integrate the velocity. And the velocity is this vector over here, 80, negative 32t plus 80. And we integrate it, so we get 80t plus some constant. The integral of negative 32t is negative 16t squared. The integral of 80 is 80t, and then plus another constant. Again, to figure out what the constants are, we use the initial conditions. And the initial conditions tells me that, let's go back, the initial position of the ball, if this is the origin, it was 0 on the x and 3 units on the y. So the initial position of the ball, 0, 3. So then we go back down here, and 0, 3 is r of 0. We plug 0. So this term cancels, these two terms cancel, and we get C3 and C4. So this tells me that C3 is 0 and C4 is 3. So finally, we got the position function, all right? So now we can get to the other questions. Let me get more paper. And so we can get to the other questions. What are the other questions? So let's summarize. We have, there's the position of the object and the velocity. I'll write it here, it's easy. It's just the derivative of that, negative 32t plus 8. So there's the position and the velocity. So here are the other questions. First question is, show that the trajectory is a segment of parabola. Well, that's kind of easy, right? Because see over here, we now have the x component and the y component. So the x component, is 80t, and the y component is negative 16t squared plus 80t plus 3. So you can solve for t. It's like eliminating the parameter. We did this when we learned about parametric equations. So t is x over 80, and then plug it in here. So then y is negative 16 x over 80 squared plus 80 x over 80 plus 3. And this is y equals negative 16 over 80 squared x squared plus x plus 3, which is obviously a parabola, right? That's the equation of a parabola. So that's the end of that one. Part C says, assuming a flat playing field, how far does the ball travel horizontally? How far does the ball travel? All right. And how do we do that? Well, how do you figure? Well, let me put this one back here so we know what the R is. So think about it, right? We need to know when is it that the ball is going to hit the ground, right? And that's easy. It's going to be when this is 0, right? So the ball will hit the ground when y is 0, right? This y, i.e. negative 16t squared plus 80t plus 3 is 0. And well, we need to solve this equation, and then you find the t. Now there's going to be two t's here. This is not an easy one, so you would need to use the quadratic formula. So the answer to this one, once you multiply by negative sign to make it so that the leading term is positive. So there's two solutions, 80 plus or minus b squared, so that's negative 80 squared minus 4 times 16 times negative 3 divided by 2 times 16, that's 32. So I'm not going to give you the details. So there are two solutions here, one negative and one positive, and the negative solution obviously doesn't work because that will be in the past, right? Before you hit the ball, makes no sense. So we only keep the positive solution. So only keep the positive solution. So t equals 80 plus, so like 6,400 plus 12 times 16 divided by 32. It's about, according to the book, 5.04. So after about 5 seconds, the ball hits the ground. And then to figure out how far it landed, you just plug that into the x, right? The x was right here, 80t. So the ball travel x equals 80 times t, which is 80 times this number if you want it precise. And if you want an approximation, it's about 80 times 5.04, which is about 403 feet. All right. Next question. What is the maximum height of a ball? How do we do this one? Well, for this one, what we could do is, I mean, there's two ways you can do it. You can figure out the vertex of that parabola, right? Because we know it's a parabola. So the highest point will be the vertex of a parabola. And if you know, remember your analytic geometry from high school, you can find the vertex if you complete the square and do all that. That's one way. But if we want to use calculus, the better way would be to use let me scroll over here, the velocity, right? What do we know about the velocity when you reach the highest point? What do we know about it in terms of going up and down? So yeah, the y component will be 0, right? Daniel answered, but the x component is not. The x component is 80, right? The ball is still moving forward. But with respect to going up and down, the ball goes up, then momentarily is suspended in the air, and then it goes down, right? And that momentarily suspension time would happen where the y is 0. So that's how we can find when is it that the ball achieves maximum height. So the ball achieves max height when the velocity is 80,0. And the velocity was given by -32 plus 80, then that has to be 0. And if you solve for t, this tells you that 32t is 80. So that means that t is 80 over 32. This is 16 times 5, and this is 16 times 2. So this is 5 halves, so that's 2.5. So right after 2.5 seconds, we have maximum height, right? Exactly as at 2.5 seconds. So then what is that height? So the height at that point is, how do we know the height? Well, then we go to the original expression for the r, right? Here it is. Here's the original expression for the r. This is the x, and this is the y. So we use this one. So it's going to be -16, 5.5 squared, plus 80 times 5.5 plus 3, whatever this is. 25 fourths plus this is 80 times 5, that's 400, that's 200, that's 3. This is -4 times 25, that's -100 plus 200 plus 3. So this is 103, and these are feet. So that's the max height, 103 feet. And then the last question. Last question. Over here. Part E is, the question is, does the ball clear a 20-foot fence that is 380 feet from home plate? So is it a home run or not? So does the ball clear a 20-foot fence that is 380 feet from home? Right? So in other words, let's do a little diagram. So we have the ball, 3 feet, we hit it, follow the parabola, and then somewhere over here there's a fence which is 20 feet, and this is 380 feet distance, and we don't know if it's gonna clear it or not, right? So how can we tell? Well, we can find where is the ball when the x is 380. If the ball is bigger than 20 with height, then it clears the fence. If the ball has less than 20, then it's gonna bounce on the fence. Is that clear? So how do we do it? Find out find out the height of the ball when x is 380 feet. Okay, and what was the position of our ball? Our position was, so let me write it here. Here's our position, 80t negative 16t squared plus 80t plus 3. So then we find out when 80t is 380. So the x is 380. So then we can figure out for t. That means t is 380 over 80. And this simplifies. And this is 38 over 8. So that's 19 over 4. So that's 1/4 less than 20 over 4. 20 over 4 would be 5. So this is 4.75. So that's after 4.75 seconds, the ball has traveled 380 feet. How high is it? So then to find the height, then the y is this, will be negative 16, 19/4 squared plus 80 times 19/4 plus 3. And we just need to check if this number is bigger than 20 or less than 20. Right? It's negative 16 over 16 times 19 squared plus 80 times 19 over 4 plus 3. The 16s go away. 19 times 19, I think, is 361. 80 divided by 4 is 20. 20 times 19 is 380, and then plus 3. So this is, this minus that is 19 plus 3, 22. 22 feet is how high is the ball is when it traveled 380 feet. So it clears the wall, right? The wall is 20 feet, so it goes 2 feet over the wall. So it's a home run. So answer, yes, the ball clears the wall, clears the fence, because 22 is bigger than 20. And that's the end of our problem, right? As you can tell, none of these was really calculus, was just, you know, using all these expressions that we worked so hard last class to figure them out. Well, there was a little bit of calculus, how to find out the maximum height, right? That concept that the derivative on the y direction is 0 at that point. So the ball is just suspended for a brief moment, just for an instant. It's suspended in the air. Very good. So that is it. We're gonna go now into the last section. We're gonna cover last section of the entire semester, 14.4, and this is length of curves. And fortunately, we in a sense had already, so this is gonna feel a little bit like a review, because we've done it already, at least in the plane. So we didn't do it in space, but as you're gonna see very, very quickly, the procedure is exactly the same. So let me just recall that we've already done this. So recall that we already had done it for curves in the plane. So if you have, and also with polar coordinates, if you remember that. So if you have a curve in, well, these axes are so crooked, let me do them again. If you have a curve in the plane, some curve like this, parametrized some way, right? So if you have a parametric equation where x is f of t and y is g of t, and where t goes from a to b, then the length of the curve was given by this integral. We did this work before. It's the derivative of f squared plus the derivative of g squared, square root of that integral between a and b. So we had done this before. And not surprisingly, the same way in which we figured it out. So that means you can also do this for a vector equation, right? If you write a vector RT, and you simply write it as f of t, g of t, the same thing works, right? And now I'm gonna go to the book and show you how the exact same thing is going to happen for 3 dimensions. So this is what we were just discussing. So this part over here, I'm gonna mark it in a second, is the formula I just wrote to you in the page. And here's the new thing. So if you have now a new 3-dimensional vector function, this green one that I'm highlighting right now, well, it's not surprising to think that the length of the curve is going to be given by this new brown one that I'm highlighting, okay? Compare to the red one, and you see how it's the exact same formula, but now we have f prime, g prime, and h prime. So the square of the derivative of the f, the square of the derivative of the g, and the square of the derivative of the h. All right. So that's our definition, and we'll use it to figure out a few examples. And you'll notice that it's essentially the same type of ideas. The main difficulty, same as with any of these arc length integrals, the main difficulty is that the integral may be complicated. The integral will have a square root, and it's very hard to get rid of that square root, which makes those integrals challenging. But the part of figuring out what is the integral that provides the arc length, that part will be easy. So let's take a look at some problems, some that we can actually do. Let's go to next page, page 898. We're gonna go to example 2. And there's a nice picture right here on the left, which is what we're going to be doing today. So let me put the picture. Here's what the question says. It says, flight of an eagle. It says, an eagle rises at a rate of 100 vertical feet per minute on a helical path given by, and I'll show it to you in a moment, where this is a figure. So the eagle starts right here at the bottom and starts climbing. And at the same time that it climbs, it sort of goes in an around, right? It's sort of going around and around, and it stops over here. Well, I messed it up at the end. It's difficult to draw with the mouse. But that's the path of the eagle, and you can see it right here. I'll scroll to the right here. So here's the problem. It says, an eagle rises at a rate of 100 feet per minute on a helical path given by, and this is the r of t, 250 cosine t, 250 sine t, 100 times t, where r is measured in feet and t is measured in minutes. How far does it travel in 10 minutes? That's what we need to find out. How far does it travel in 10 minutes? So in other words, what is the length of that path that I showed you on the picture, right? Between time 0 and time 10. So what is the length of the path from 0 to 10? From 0 minutes, from time equals 0 to time equals 10. Let's do it. So this is a question we want to answer. And here they are. 250 cosine, 250 sine, 100t. Okay? Now, just like we said, right? How do we do it, the length? It's gonna be an integral. From where to where? Easy. From 0 to 10. That's super easy. And then square root, big square root of what? The derivative of the x squared, the derivative of the y squared, and the derivative of the z squared. All of that with respect to t. Okay? Let's do it. What is the derivative of the x? Right here, 250 cosine. So the derivative of cosine is negative sine. So it's negative 250 sine t, quantity squared. Now the derivative of this one will be 250 cosine t, quantity squared. And last, the derivative of 100 t, which is 100 quantity squared. All of that, right? Next, we try to simplify. Here, actually, we're gonna be lucky because this will be 250 squared times sine squared t plus 250 squared times cosine squared of t plus 100 squared. And we know that sine squared plus cosine squared equals 1. So this part over here is sine squared t plus cosine squared t. This is 1. So all of this is now the integral from 0 to a 10 of 250 squared plus 100 squared. Not that bad, right? And it's not an exact number, but it's just a constant, right? Whatever it is. So it's, let's see, 2500, that would be 625. No, that's not right. That's, yes, it is. And then 2 zeros plus 100 squared, which is 10,000, whatever that number is. So it's 10,000, and this is 62,500. So it's just a constant that we can take out of the integral, 72,500 times the integral from 0 to 10, right? And then that's it. We were lucky. This is a very simple integral. It's just this weird constant times t from 0 to 10. So the answer is this constant times 10 minus 0, or 10 times this square root. And I would leave it like that, right? I mean, you can try to approximate it if you want. This turns out to be about 2690, and that would be feet. Okay. All right. So that's the end of that one. And there's a few others. So they're all going to be examples like this. The main difference is that now instead of having two, so let's go back over here. Instead of having the x and the y only, we have the x, the y, and the z, right? And an additional one to be that we need to concern ourselves about. Okay, so that is essentially it. I don't think we need to, so we should just work on a few additional examples, but there isn't anything of substance here other than that. So let me, let's see if we can do another example that is a bit more challenging. And we don't have too many, actually. They're all, unfortunately, the ones you have on the book are integrals that you will be able to do, but let's take a few, a look at a few of them. So let me go to the book, okay? And let's pick some here. For example, let's see if we can do about number 23. Now that was gonna be easy actually, but how about 26? 26, it says For the following trajectories, find the speed associated with the trajectory and then find the length of the trajectory on the given interval. Right, and we're gonna do 26. So for 26, our trajectory is given by r of t equals e to the t sine t, e to the t cosine t, and e to the t between 0 and ln2. Okay, that looks complicated. We'll see if we can do it. So it says find the speed of the trajectory and find the length of the trajectory. Find speed and length of the trajectory. Good. Let's switch to the page. Yeah, Michael is writing, what a short lesson. And yeah, you're right about that. There's an extra part, which is using the arc length as a parameter, but that's not emphasized for our final. So, I mean, we could go over it, but I would feel weird emphasizing it when it's not going to be there for the final exam. So we may as well practice the things that will be included in our next exam and on the final exam. But yes, this is, I kind of like it because it's the end of the semester, so we want to have something that is light, in my opinion, to finish with the desire to study and do hard on our final exam. So yes, very short indeed. So let's do this. Find the speed and the length. So let's recall, very important. So what is the speed first? So the speed is the absolute value of a velocity, the magnitude of the velocity. So recall that speed is the magnitude of the velocity. So let's figure out that first. So what is the velocity? The velocity is, we need to take the derivative of each component, right? So it's the derivative of this one, the derivative of this one, and the derivative of e to the t. And some of these are easier than others. Here we need to use the product rule. So it will be the derivative of e to the t times sine plus e to the t times the derivative of sine, which is cosine, comma, the derivative of e to the t cosine t, e to the t times cosine plus e to the t times the derivative of cosine, which is negative sine. And last, the derivative of e to the t. Okay, so that's this over here is the velocity, but the speed is the velocity is a vector, right? Remember, it's not only it not only tells you how fast you're going, it tells you in which direction you're going. That's awesome. Remember, with all the animations I show you in the last couple of classes. So, but the speed, it only is if you only care how fast you're going. Doesn't matter which direction. So for that, we just need to do the absolute value of that. So that's the speed. And that, when I said the absolute value, I really mean the magnitude, because this is a vector. So we need to square this one, square the next one, which is the same as the previous one, but with a minus here. No, this one has, did I write it? Oh, I flipped the order, but it doesn't matter, right? So from here to here, I put this term first and that second, but it's the same. And here, because that way they match with this second one that I'm writing. And so that's the speed, right? And if this was a final exam or my test, I leave it like that. That's it. Now, if you want to do that speed for something else, maybe you should simplify it. And in this case, it actually simplifies nicely. I'll show it to you. So when we square this one is e to the 2t cosine square plus 2 times e to the 2t sine t cosine t. That's the middle term, the product of these two, plus the square of the second one, 2t sine squared t, plus the square of this one, the middle term, but now with a negative sign. The square of the last term. And last, the square of this one. And that's a big, gigantic square root over everything. And fortunately here, lots of things cancel. So first, or simplify, this double term cancels with that one because it has a negative sign. And then these are the same. And I have sine square and cosine square. So that's good because this is 2e to the 2t times cosine squared t plus sine squared t. That's already these two together and these two together. And then we have another e to the 2t. This is obviously 1. So now you have 2e to the 2t plus another e to the 2t. So that's 3e to the 2t. And you can now take the square root of 3 and take the 2t with the square root, becomes just e to the t. And voila, right? Not too bad. So the speed is a square root of 3 times e to the t, and is a nice expression, right? It's increasing speed, as you can tell. This particle is moving faster and faster and faster, really, really fast. Okay, so that's that part has nothing to do with arc length. That was the first part of the question. The second part of the question is, let's go back to where R is, right here. The second part of the question is to find out the length of the trajectory, right? So we're done with speed. And now the length of the trajectory, for that, we need to now integrate, right? So let's do it. So I'm gonna write it over here, is going to be, let me put it like this. Here we go. So it's going to be the integral from 0 to ln2 of the square root of the derivative of this one squared. Hey, oh, we already did the derivative, right? And so it's the derivative. So let's go back to what we did. Does this help us in any way, right? See, this little observation. We did the velocity. Does that help to figure out the length? And notice what is the arc length of the velocity. So in general, so this is actually something useful. So recall that. See, if you want to do this, the square root of the derivative of the x square plus the derivative of the y plus the derivative of the z square, isn't that the same as the magnitude of the vector derivative x derivative y derivative z? Isn't that how we go how we get magnitude? Yes, right? That's correct. And this is exactly the derivative of r. So this is the magnitude of r prime. And that's the derivative, the magnitude of the velocity. So this is the speed. Okay, so that's a different way of doing these arc length formulas. So an alternative formula, if you want, it's the same one, but it's just using different names. The alternative formula is that the arc length is from A to B, and you're integrating the magnitude of the velocity, right? So in other words, to get the arc length, you can integrate the speed. Integrate the speed. So that helps a lot, right? Because here we don't need to redo all the work. We only need to integrate square root of 3e to the t for the problem we were doing. So we take the square root of 3 out, and when we integrate, the integral of this is this. And we're doing it from 0 to ln2. So we plug ln2, we plug 0. Remember that e to the ln2 cancel each other, so that's 2. and e to the 0 is 1. So the length is actually square root of 3, believe it or not. Okay, questions? All right, let's see, we have about 20 minutes or so. So let's take a look at another problem. 19 also has E. No, hold on a sec. How about, see, some of these are not even in 3 dimensions, right? They're only 2 dimensions, so it makes it, well, actually, okay, let's try one of those. Maybe it will be a bit more challenging. How about 18? So let's try 18. It says, find the length of the following 2 and 3-dimensional curves. So let's do 18. And for 18, we have r of t equals t squared over 2, 2t plus 1 to the power 3/2 over 3, between 0 and 2. All right. Let's change to the page. Good. So we could follow along from what we said. So here's the length. And the length is the interval from 0 to 2 of the magnitude of the velocity. So that's integrating the speed, which is the same as the magnitude of r prime. What is r prime? The derivative of t squared over 2, that's t. And the derivative of this quantity over here, the 3/2 comes down. And it will be 2t plus 1 to the power 1/2 times the derivative of 2t plus 1, which is 2. Everything square. All right, so that's just the derivative. Right. Now, to figure out its magnitude is where we're going to square each one of the components and add them. So let's continue over here. So it's the integral from 0 to 2. Let's first simplify this because there's a lot of things here. So this 3 goes with this 3 and this 2 with that 2. So it's t and then 2t plus 1 to the power 1/2. All right, fine. Now let's get the magnitude of that. What is the magnitude? It's the square root of the first one square plus the next one square. Okay. So this is t squared. And then here the square and the 1/2 cancel each other, so we get 2t plus 1. And again, we are really, really lucky that this ended up being a perfect square. We can factor it, right? Otherwise, we would be in problems trying to integrate this. Well, actually, we wouldn't because we know trig substitutions and all of that, but it could be a difficult integral. In this case, it's not, because this is simply t plus 1 square root of that. And the square root cancels the square with an absolute value. But between 0 and 2, this is positive, so we don't need the absolute value. And now it's easy to integrate, right? T squared over 2 plus t, and we're doing it from 0 to 2. Plug 2, so that's 2 squared over 2 plus 2 minus plug 0, 0 squared over 2 plus 0. And this is 4 divided by 2 plus 2 minus 0. So 4. The length of the curve is actually 4 units. Okay? All right. Questions? Okay. Okay. So let me now let's highlight the rest of the days that we have So we're having an exam coming up soon. So our next exam is on Thursday. So April 30 is where we're gonna do our last exam. Our last exam is going to work the same way as we did our previous one. So we're gonna meet here the date of the exam. We're gonna have a review. We're gonna have review 2 days, tomorrow and the day after. So 2 days for review. Start working on your questions. We're gonna have 2 days for review. Today, not today, Wednesday, tomorrow, and the day after, and Thursday. And on that day, Thursday, the same as before, we're gonna, right after class, a bit after class, so at 1 p.m., your exam will be available just as the same way we did the previous one, 24-hour period. The format of the exam will be similar, and you'll upload your solutions the same way. You guys did it very, very nicely with the previous one. I didn't have any problems at all, so I don't anticipate any. If you guys just work it out the same way, everything should work out. So that's for this week. Then next week we have Monday, Tuesday, Wednesday, and Thursday. Then the entire week for review. So we're gonna review the entire semester. We're gonna work on the sheet available for sample problems for the final exam, and I may even try to see if we can get, although it will be different anyways. The final exam will also be a 24-hour exam, with the difference that it's going to be, you know, the same coordinated exam for everyone, etc. You may have to take it into not this Canvas, not our own Canvas page. Maybe it will be available on the math department's 150D page, right, that you have access to as well. But don't worry about it right now, because I don't know the details just yet, and instructions will be provided when the time gets close. So, but I just wanted to give you an overview of what is left for us to do. So next 2 classes review, exam on Thursday, and then the entire next week review, and final exam on Saturday. Okay, that's pretty much the overall summary. Now I want to, let me see if I have it right here, look at the review sheet. Let's have it somewhere in here. Don't seem to have it right there, but what I do have, oh, I do have it. Okay, great. So let me show it to you. So these are the problems we're going to be working from to review. There we have the link on Canvas, you know it, and there's also the solutions available online. So we'll go over all of these questions to review. In fact, we'll start tomorrow. We'll start reviewing the ones that are relevant for our upcoming exam. So our upcoming exam starts right where we, let's see. So we did right here. So in 13.1, so our exam will cover chapters 13 and 14. So these are initially the ones we are going to review tomorrow and the day after. So 13.1, 13.2, these types of problems, you know, given a vector, find a unit vector pointing in the same direction, spheres and equation of a line in 3 space, finding the angle between 2 vectors. You use the dot product for that. Finding the cross product, or the area of a parallelogram, or the area of a triangle. You use the cross product for that. Find a vector that is perpendicular to 2 other vectors. That would be also the cross product. these problems about some object that has a specific acceleration and a specific velocity, and you need to find out all these other properties of it. And finally, arc length, right? This 14.4, which is this little example that you see right here at the end. Okay, so we're gonna go over those. Now, if you wanna be specifically more prepared, you can also take a look at, let's see if I have them right here. So we have a list of problems. Let me see, and where is it? So we have our list of problems from, yeah, no, that's the one we just opened. Okay, so we have in our Canvas page, maybe I'll show you that one. So hold on just a sec. So we also have a list of problems from the book, okay? And that is important because right there in the problems from the book, we know for a fact that the entire final exam will come from these problems. Okay, so I'll show you in a moment. So if you go to our Canvas page and you click on Files, where we have, I have the files available to you. Let me show you right here. If you go to Files and you click on what is it? Homework, this first file, HW Spring 2019, you get a PDF, will appear on the screen in a moment, and this has all the suggested problems from the book. Okay, so if you want to be absolutely prepared for your final exam, take a look at this list of problems. If you can do all of these over here, then you're going to be set. You will be able to be very, very successful. For sure, you're going to ace the exam if you know how to do all of these problems that you see on this list. Okay, so those are your resources available. Work on this list of suggested homework problems, and also work on the list of sample problems, which I think will come up right here. So you'll see coming up here. Yeah, that's right. Even though it says Spring 2018, is the exact same list of problems, all right? I just didn't want to upload the new file. The one that has the right Spring 2020 here is the exact same one. I don't think the department has even updated the one that is on the regular web page. Okay, so that's our plan for the upcoming classes and for our last exam, for our preparation for the final exam, and for the way the final exam will be conducted. Okay, are there? Okay, so I see some questions. Alexandro just asked, how much time will we have for exam for 24 hours? It will be 24 hours, the same as our previous one. And I think the final exam will also be 24 hours. So same format. Any other questions? Good. So then I'm gonna log off shortly. Let me remind you also that, from what section to what section would be the exam for? Good. So it's the chapters 12 and 13 is what is included. So the entire, I'm lying here. Sorry, not chapter 12. So chapter 12 we already covered. Chapters 13 and 14, right? So starting from 13.1 all the way to the sections we covered. I mean, not the ones we didn't do 14.5. So make a note of that. We don't do that one. And we didn't do 13.6 or 13.5 either. So only the sections we covered, of course. So it's 13.1, 13.2, 13.3, or 13.4, and 14.1, 14.2, 14.3, and 14.4. You can also take a look in our page. Where is it? In our, let me share it to you. If you go to our page, and let's close this. Right, and home, when you have your calendar, in your calendar, I marked the sections we covered every particular date. So it's going on. Okay, so right here, and you can see it. So we had our exam 3, and then for our next exam, we have all of these sections included for our next one. 13.1 all the way to 14.4. Okay? Okay. Very good, guys. So I'll see you guys tomorrow. Remember, start studying because we're going to review for chapters 13 and 14. Stay safe.